Now there's a lot of similar things that go on as soon as you've got higher powers of x and they're all odd. So we've just looked at cubic curves, and curves like y equals x to the power of 5, x to the power of 7, x to the power of 9, etc., all have the same basic shape as y equals x cubed. The only difference is that where y equals x cubed just has a very short flat spot, the higher the power that you have, the bigger that flat spot is, and yet when it does go shooting up, it goes shooting up or down much more steeply. And that makes sense. If you just sub something in to y equals x cubed, let's sub in x equals 2, say, then on this curve, when x is 2, y would be 8. If we look at the next odd power, like y equals x to the power of 5, and we plugged in that same x value of x equals 2, well, 2 to the power of 5 is 32. So that's a lot bigger than 8, and that explains why we only have to go across a little bit before we've got a y value that's so high, and that's going to make the curve really steep. Slight disclaimer now, neither of these are drawn perfectly to scale. So if you want to look at how steep these curves are or how big the flat spots are, go on to desmos.com and just type in y equals x cubed, y equals x to the 5, 7, 9, and have a look at the shapes of those curves. Now we saw with the cubic curves that when we added other terms like x squareds or x's and other numbers, it gave the curve wobbles. And in fact, it turned it from being something that just had one horizontal point of inflection to then still having one point of inflection, but a wobble in it. So a complex cubic curve looks like this, whereas the basic one is more straightforward. Well, similarly, the complex versions of higher powers of x, like x to the power of 5 or 7 or 9, and we're looking at odd powers here, just have more wobbles. How many wobbles? Well, they have 2 extra point of inflections. So every time we go up 2 in the power, we go up 2 points of inflection. So I think of what a cubic curve looks like, and I know it sort of goes up and then down and then up again for a complex one. So y equals x to the power of 5, and I've put ... here to show the formula would have more things in it, and it could even have a number out the front. It has this basic shape, up, down, and then up. Now, how high are the ups and how low are the downs? Well, you don't know that yet, but you look for intercepts as a way of locking in where it sits. So this is one that has the highest power of x being 5. For 7, you just do another wobble. So count your wobbles here, and you can see I've got up, down, up, down, up. So the next one would be up, down, up, down, up, down, up. It's got that basic shape. And so on and so forth. For x to the power of 9, I'd need to do another up and a down. Now, having a look at points of inflection, we're concave down here, but this section's concave up, so there'd be a point of inflection here somewhere. Concave down, up, but then concave down, there'd be another point of inflection around here. From concave down to concave up, there's another one somewhere here. So you can see that this one has got 3 points of inflection. Whereas as soon as we do an extra up-down, that's another 2 points of inflection. I can quickly and easily spot where the concavity is changing here and just get it roughly right. And I can see that this curve has actually got 5 of them. So knowing how many wobbles you're looking for helps you a lot. Let's have a look at how we'd graph a couple of these. All right, this first example, let's just count the powers of x here. If we expanded this out, and we are in no way wanting to do that, we've got x times x times x times x times x. So this is x to the power of 5. Now, at the front, there's no negative here, so this means we've got a positive one. So it's going from low, wobbling, and going high. Now, let's put the points in that it's going to wobble through. If we let y equal 0, imagine it there, then one of these parts must have been 0. So either x was -4, -3, so we've got a spot here, 0, 1, sorry I don't have much scale here, or 5, 2, 3, 4, 5, let's put 5 there. Okay, now we've got some points that we need to go through. We've got 5 points. We can just literally do some wobbles and make sure it goes through all the points. So it's starting low and it's finishing high. So we go up, down, up, down, up. It's pretty fun to draw. Now, all we need to do then is check if we need to look for a Y-intercept, but we don't because, of course, if it's gone through here, we've basically already found it. Let's go again. Look for the highest power of x that you've got. Now this one I can spot has a double root. So it's basically like this is an extra one that I could write x plus 1 again. But I also know that when it gets to this point here, it's just going to touch the x-axis and not go right through. So I can see that I've got 1, 2, 3, 4, 5. So my highest power of x is going to be x to the power of 5. And this negative out the front means we're starting high, we're going to do some wobbles, and then we've got to finish low. So let's put in all our x-intercepts. We have 1. Now remember, we're imagining letting y equal 0 and think, how could that happen? Well, negative 2 can't equal 0, it's negative 2. This part could equal 0 if x is 1. This part could equal 0 if x is negative 1. Now that one's the double root. I'm just going to put a d there to remind me. And x is minus 3. We've got one that goes through there, and x is 2. So notice here, sometimes they'll kind of be in increasing order or decreasing order. Other times they'll just be jumbled up. It really doesn't matter. You find your spots. Now I know I'm starting high, so I need to come towards this one and through it that way. This is the double root, which means that when I come up to it, I need to go not through it, but actually just touch it. Now I need to go through this one, back down that one. Oops, I didn't quite go through that, but you get the idea. And that's it. Now the only other thing I need to show here to make it complete is this point on the y-axis. So we do that by letting x equal 0. Now this is a long one, potential to make a mistake, so how about we just write out what we've got? Negative 2 times, now we're letting x equal 0, so I'll have negative 1, 1 squared, 3, negative 2. So I've got negative 2 times negative 1, that's 2, times 1, still 2, 6, minus 12. And this point here can be minus 12. Now you'll see that obviously my scale must be different on my x and y axis. That's fine. Or if you'd found it first up and you'd put it way down here, minus 12, and you'd made it go right down to that and up again, that's fine. But mathematically these two drawings are equally good because there's nothing to say that you have to have the same scale on your x and your y axis. Now when we look at higher powers of x that are actually even, like y equals x to the power of 4 or 6 or 8, 10, etc., etc., we see that we get a lot of the same principles happening as we did with the odd ones. So we know that y equals x squared is a parabola, and that we know that if it has a number in front of that, it will stretch it, and a negative number in front will flip the whole thing upside down, and it will be an upside down parabola. But when we have a higher even power of x, it makes sense that the flat spots are going to be flatter for longer, and the steep sections of the curve are going to be even steeper. And that makes sense if you just consider a point on the curve. If you're going to have something like when x equals 3, what's y? Well, 3 squared is 9. So if you came out 3 notches here, you'd be right up at 9. Whereas over on this curve, if x equals 3, then 3 to the power of 4 is 81. So you can see why it would go shooting up much more steeply. And when we look at the complex ones, and by that I mean the ones that might have lower powers of x as well, so perhaps it might be x to the power of 4 being the highest power of x, but it might also have some x cubeds, some x squareds and whatever. Well, we just get extra wobbles, just like we did with the high odd powers of x. And at this stage of the course, we can only graph these if we're given to them in factorized form. So let's have a go at this one. If we were to expand this out, and we are not going to, we would get x to the power of 4 as being the highest power of x. So that tells us what type of curve it is. They call these quartic curves, but you can just think of it as x to the power of 4. Now, x to the power of 4 is a bit like x to the power of 2. We know that x squared is a parabola, and if it's a positive one, which we can see here it is because there's no negative number here at the start, it starts high, finishes high. So if it's got extra wobbles but it needs to start high and finish high, the basic shape needs to be like this, but without V's in it. I should have drawn that more of a curve. So it's going to go up and down a little bit, but it's going to start high and finish high if it's a positive one, or it's going to start low and finish low if it's a negative one. So let's draw up our Cartesian plane here and just put in our x-intercepts. If we let y equal 0, that would only happen if one of these parts was 0. And that could only happen if x was negative 1, 2, 5, or negative 3. 1, 2, 3. It's not a great scale, but you get my point here. So now we just have to make our graph go through these points. It's starting high and finishing high because it's a positive one. So I'm just going to have fun here drawing it down, up, down, up. And once again, even though these are little like parabolas, they're not parabolas. So in between two intercepts, you can't be sure that a hump will be symmetrical. I mean, I've sort of drawn them roughly like that. They could be quite wonky. So there's no guarantee that, say, the middle of this hump here is halfway between the 2 and the 5 with at x equals 3.5. We don't know. So just go ahead and draw in a wobbly shape that's roughly right. Now we need to find the y-intercept, and we can do that by letting x equal 0 all the way across. So we'll have 1 times -2 is -2, times -5 is 10, times 3 is 30. And once again, my scale is different on the x and the y-axis, completely fine. Let's have a go at another one. Now, the first thing that's jumping out at me here is that this is a -1. Now, what type of curve is it? Let's work out what the highest power of x is. It's got 2 of these double roots in there, so you've got to watch out for those, because that means we've got x plus 1 times another x plus 1. So if I was to expand this out, and I definitely am not going to, because that's really not going to help me, I would have 1 power of x here times 2 more there, so 1, 2, 3, 4, 5, 6. So this is x to the power of 6 as my highest power of x. So if x to the power of 4 had a wobble in it like that, then x to the power of 6 is going to have an extra wobble. It's potentially going to have this sort of shape. So it's going to need to go down and up and down and up and down and up. Oh, but it's a -1, so it needs to do the other way around. It needs to go up, then down, then up, then down, then up, then down. And it's going to finish on a down at both ends. So let's put in our x-intercepts. We find those, x-intercepts, yeah, we put those in by letting y equal 0. And that happens when one of these parts is 0. So either x is 0, it goes right through the origin, or -1, and that's a double root there, 2, and that's just a normal root, or 3, and that one's also a double one. So let's start from one end or the other. It doesn't really matter. We'll start at this end. We know we need to go up and through. No, this is a double root, so we don't want to go through that one. We want to just touch it. So it needs to just touch there and then go down again. Then it needs to go through this one, so it's going to have to do a quick turnaround to get back up again. And then it's going to go down through this one, make it go up a bit and then down. And then this last one is a double root, so we've got to do a quick turnaround before we go up, touch it, and then go down again. So now we've got something like that. Okay, a little bit wonky, but you get the idea. So you can see these are quite fun to draw. You pretty much can see the points it goes through. You know whether it goes through them or whether it just touches them and glances off again. And then you just draw in your wonky shape. It's mathematically not perfect, but at this stage of the course, with this information that's given and without being asked to show any of the turning points or anything, this graph is mathematically good enough for what we need it for.